Welcome to another episode of brainsmatter. And today we have Dr. Jürgen Knödlseder once again. Thank you for joining us today.
Thank you very much for the invitation.
Well, last time we spoke about gamma ray astronomy, some really interesting facts that you told us there. Today, it's going to be a little bit different. So you've got a background as an astrophysicist, as a scientist doing a lot of research work. You also have a keen interest on the environment and astronomical research, isn't that? So can you give us a little bit about the background of that? So firstly, what prompted you to start looking at that? And secondly, what you're looking at right now?
Yeah. In fact, if you follow a bit what's going on in astronomical literature, you may have recognized that there are some articles around about the carbon footprint of astronomy, of communities, of different labs, and so on. So I think there's a general movement in the astronomical community being also concerned about their environmental footprint. And it's maybe tied to the fact that, I mean, for me, astronomy is part of nature. I mean, it's of course not the nature on Earth, but the nature of the universe, and also it's we all know how rare life is in the universe. At least so far, we haven't found any other place where life exists. We know over 5,000 planets today, exoplanets. From no planet we have any clue that there's life on this planet, and at least for those planets we explored in the solar system or their moons, we haven't seen any evidence for life either. So it's a very rare thing, and I think we all astronomers have the feeling that we really have to protect the life. And if you read IPCC reports or other reports, I mean, you really see all the threats on life on Earth. And this, of course, makes you think. And so the question we had in Toulouse at our lab at IRAP was also to understand, okay, what's our share? What's our footprint? And one obvious thing that was identified very, very soon was, for example, the professional traveling, which is done, of course, a lot by plane. You know, I mean, when you do astronomy, you sit a lot on planes. It may be because you go to conferences all over the place, all over the world. I mean, traveling eventually very far for maybe giving a 10 minutes speak on the other side of the planet. But also, I mean, if you work on projects, and I worked a lot on projects, I mean, on basically new instrumentation, like making satellites, but also if you make a ground-based observatory, it takes you years, very often decades, and I don't know how many meetings to get these projects, to put these projects in place. So it also involves a lot of traveling. So traveling was identified as a important contributor to our carbon footprint, but we at IRAP had the ambition to try to get a full picture, right? To look at all different aspects of astronomy, and so also explore other things that we need and we do in our daily life, in our astronomers' life, that eventually have a carbon footprint.
How did you estimate the carbon footprint of your particular lab?
So it's very important, if you do this exercise, that you do it right. And by doing it right, I mean that you follow a recognized standard. So what we did in our lab, we decided first to take a training on how you do a carbon footprint estimate correctly, and we followed when we are a lab in France, so we followed the French standard, which is called the bilan carbone, and this was extremely interesting because it answered all the questions that you typically hear. How should I mean, what do I need to take into account when I make an assessment? How should I do the calculation, and so on? How should I attribute some carbon footprint to my lab if it's shared among different institutes and stuff like that? So we got answers to all these questions, and then we were pretty easy, basically, of doing this kind of exercise. Now, if you do that, the first thing you do is you draw basically a map, flux map, what's going in your activity or in your lab and what's going out of it. And so just to define basically the boundary of your system. And then you need two things, in fact. Then you need what's called activity data. They say basically how much do you fly, how much energy do you use, how much heating energy do you use, and so on and so forth. And then you need emission factors, which tell you how much CO2 per activity, per amount of activity. So how much tons of CO2 per kilometer of flying or whatever, or per kilowatt hour of electricity spent. So, and collecting all this data, this was in fact the most time-consuming part, because I mean, it's not always, I mean, it's not easy to get this data. I mean, sometimes somebody has an electricity bill and you can get these numbers, but sometimes it's not so obvious. So some data we get by using a poll, by asking just people, for example, how do you come to the lab? Do you ride a bicycle? Do you go by public transport? Do you have a car, and so on? So we collected all the data, and then we were basically done. But then there was one question: what to do with our observatories? Because we use in our daily life a lot of data coming from observatories, from satellites, but also from observatories on the ground. And formally, I mean, we are also somehow responsible for these emissions, because, I mean, without astronomers, these observatories won't exist. Sometimes we build them, sometimes we operate them. So it's obviously that we have to take this into account. And then we started our work on basically estimating the environmental footprint, or the carbon footprint specifically, of the observatories, and this was never done before. And what we used there, I mean, of course, you have not very detailed access to information about these observatories, but what you can always do, and that works in fact quite nice, is use what's called a monetary method. And in the monetary method, you relate in fact the carbon footprint to the cost of something. And you can find pretty nice correlations between carbon footprint of cost. So of course, it depends a bit on what you buy, and there are things that you buy that will have a larger carbon footprint for the same amount of money than other ones. But if you define by sector of activity, you get a pretty good first order estimate. So we use this method for space missions. So we take the cost of the mission, or ground-based observatory. So we take the cost of the observatory and the cost of operations. And for space missions, we did even a second thing. We said, okay, maybe it also scales with the weight of the telescope, of the satellite that goes up. So we used a relation between the satellite mass and the carbon footprint. And it turned out that the result was very close, in fact, to the estimate based on the mission cost, which shows, in fact, at the end, it was a quite robust estimate that we made. And the amazing outcome of this exercise was that the use of the observatories, of the data from these observatories, was the biggest contributor to the carbon footprint of an astronomer in our lab, but also general of the community. It's really the biggest thing. Of course, flying is a big thing, but observatories is an even bigger thing.
I read an article recently about the computational power required to run AI like ChatGPT, which is all in the news lately and so on. That's a huge amount of computational power. Obviously, there's a lot of computational power required for a lot of astronomical calculations such as the square kilometre array, which is the project that's being done in Australia and South Africa. What can we do to continue doing great research, but yet keep our eye on the carbon footprint and the environmental concerns in check?
Yeah, that's in fact that's a tough question, a challenging question, but I think also an interesting question, because I mean that's exactly what we have to do. How can we invent a research of the 21st century that is compliant with the planetary boundaries? So I think, I mean, I mentioned, for example, I mean, our professional traveling. Everybody knows we have a huge carbon footprint due to traveling. And we just have seen in 2020, during the COVID lockdowns, but we can still do quite good research without traveling so much around. So, I mean, we use a lot of Zoom now. We do, as we do now today. And you can have conferences on Zoom. And I mean, you shouldn't organize them like a normal conference. You should organize them differently. But if it's done appropriately, it can be quite interesting. I recently did a conference with astronomers for planet Earth. I don't know if you heard about this. It's a grassroots organization. It has now more than 1,600 astronomers on board that are specifically concerned about the environmental questions. And they really thought about how can you do a good online conference. And this was really a very interactive event with pre-recorded talks. We used GatherTown for then the interactive part. And I think I had more discussions in this kind of event, like in an in-person conference, which I have attended in the past, where people very often come with their laptops, do their emails on the laptops and barely listen to the talks, and for that they fly around the planet. So I think there's a big potential on the flying part. We can do a lot of good science without flying so much. And there was recently a paper about academics in France, and the field, the scientific field that is flying the most, at least in France, is astronomy. Astronomers really fly a lot, and very often to places where there's no astronomer at all. But the conferences are organized very often at very nice places. So this is the first part. As I mentioned before, I mean, the observatories is an important fraction of the footprint. Now, I think I challenge you to find an astronomer who will not tell you that there are huge amounts of archival data around that have not yet been explored. We all know this, and we have to be frank about that. And that's actually what I'm doing now since a couple of years with students here. I'm going back to my first love, which is the COMTEL telescope, which I worked on when I was a student and later on in my PhD thesis. And the interesting thing is, why go back to this old data? It's now more than 30 years old. It's funny because the students that work on this data, they were not born when the data were taken. And they like this aspect very much, because that you can really get something out of the data. And the reason why you can get something out of the data is that the field has quite progressed since that time. Because we had more gamma ray satellites, for example, the Fermi satellite from NASA, which observes at higher energies, but has revealed a lot of new information about gamma rays. And also ground-based gamma ray telescopes like HESS or MAGIC or Veritas, they have revealed a lot of new information. And now we can take this current view of our universe at high energies and go back to the old data and look if we cannot find something interesting. And I'm currently working on something. I will not unveil what it is, but it will be a big shot. And there's really quite pretty interesting stuff coming out of these data. And I think in every field you can still go back to this data and really exploit them as good as you can. And there's another phenomenon that is very interesting to observe. When you work on instruments, you always think about how can I increase my user community. So in fact, there's a competition of instruments for getting users. If you are in that situation, maybe there are too many instruments if there are not enough users for your instrument. And there's in fact somebody that wrote this up a couple of years ago in an article that showed that we are moving into a system where there are not enough astronomers compared to the number of observatories, which again, it's maybe not the most optimistic thing to do. And when you look, I mean, of course, you do projects in collaboration, but it's a lot about competition. Now in Europe, we build the ELT, extremely large telescope, will be the biggest optical telescope in the world. And the US also wants to build 2 ELTs. They call it GMT and TMT. But at the end, I mean, if you really believe that we are there to make progress in the science and we are there for humanity, you don't have to duplicate stuff. You don't have to do the same thing twice, 3 times, 4 times, just to be the first. You just need one of them. And there are other examples like sending 2 or 3 space missions to planet Venus at about the same time. What's the point? I mean, cannot you do this more efficiently? And so, I mean, by increasing cooperation and reducing competition is an important factor also to gain on all sides, not only on the footprint side, but also on interaction side and the human aspect of science, and having also less pressure to rush always from one thing to the next and to publish and so on. So this also echoes a bit what is known through the slow science movement, who advocates to slowing down and really going into depth and really trying to understand things instead of just rushing through as we do it today. And the third aspect is that I think we have to also invest money into decarbonization. I mean, a lot of the footprint comes from the energy use of the observatories, for example. And this is true for the ground-based, but also for the space-based. You need antenna to collect the data. You need data centers. Just mentioned that ChatGPT, and of course, SKA, which also will have a tremendous carbon footprint in terms of computing. And so you have to decarbonize this aspect, going to renewable energy and so on. And this means just investment. I mean, another aspect is that we need, that the funding agencies need to put more money into decarbonization. I mean, the observatories, they consume a lot of energy, the ground-based observatories, but also the space-based observatories for ground stations and data processing and so on. You just mentioned SKA that will use a lot of energy in computing. And today, you won't get any money from a funding agency to decarbonize the energy use of the infrastructure. They always want to invest money to build new stuff, but not to decarbonize. So this has to change tomorrow. I mean, they have also to invest money into decarbonization, which means that less money is available to build new stuff. But as I outlined before, I mean, that's maybe not a so bad thing. Because we have already a lot of observatories and we have a lot of data we can still work with.
So they say that science knows no political boundaries, but it sounds like we still need a lot more collaboration to happen there to get us to where we really want to go to.
Yeah, I mean, that makes you think about what's the role of science. Is it really for advancing humanity, or is it more to advancing one nation against another? Mm-hmm. Very often it's used like that. Think about the lunar space race.
The Cold War.
Exactly. And it was, I mean, formally it was planetary science. All the space race was planetary science. It was going to the moon, going to Mars, going to Venus. When you look, I mean, at the history, all these are planetary missions. So you can say, I mean, of course, it was done for science, but I mean, that was not the initial purpose. And
That's right.
and sometimes you can even question, I mean, what's really the initial purpose of the science we are doing? I mean, is it really what we pretend it is, or is it there for other reasons?
I just want to finish up on another aspect of what you're doing. You've got a bit of a political spin now as well, don't you?
Yeah, right. I mean, if you think about all these things, I mean, you can think about them professionally, but at some point also you live in some town, you have an environment, and you think, why not anything is happening in terms of whatever energy transition, having less cars, having more bicycles, and so on. So I also got involved politically, just at a very local level. And just with this aim to get things moving. I mean, really the aim is just that we make also a transition there, and environmental questions become part of our daily life there. And it's interesting because you see, of course, all these structures that are in place and that try to resist. I'm not so optimistic that politics will solve it, from what I see now from inside, which is also understandable to some in some place, because I mean, politicians are just elected in by people, and so if the people don't move, the politicians even move less than the people, because they are more conservative. They want to be re-elected the next time. So it's really tough to get things moved. So sometimes you will have little wins, and sometimes you have big losses. But I still don't give up, and I continue to push also there my environmental convictions and to try to change things.
It's always the little changes that make the big change in the end, isn't it? Anything we can do to help.
I think the biggest change is, I mean, the biggest lever arm is maybe exactly what we are doing now. Speak to people, try to convey ideas to people, and bring people on board and convince them, because I mean, that's, I think, how you can create a dynamics. I would say not so much rely on others, just try to shake it up yourself with whatever means you have, whatever lever arms you have at your disposal. But just let's talk about it and exchange these ideas and show that you're not alone on these kind of questions. And that's why I'm very happy that we have also a very good dynamics here at our lab, but also at a local level. And also like at a level, like I mentioned, Astronomers for Planet Earth, now more than 1,600 astronomers already concerned about these issues. And that's good to be part of a community and to do things together.
On that note, Dr. Jürgen Knödlseder, thank you very much. From the universe to us down here on Earth, thanks for talking to us about the environmental impact of what we do, even in the name of science.
Yeah, well, thank you very much again for the invitation. It was really a pleasure to talk to you.
Thanks for listening to the show. You can check out the Brainsmatter website at www.brainsmatter.com, and you can find all the other episodes of the show there. There's also other information on the site, such as guests who've been on the show and subscription details. You can also find Brainsmatter on YouTube, so make sure you like and subscribe if you're a YouTube listener. If you want to support the show, please consider becoming a Patreon at patreon.com/brainsmatter and signing up to one of the options there. Or you can donate either once off or regularly via PayPal. All you need to do is click on one of the PayPal donation options on the right-hand side of the website. If you have any comments or suggestions, you can leave an entry on this episode's show notes on the webpage or on YouTube, or you can send me an email. All my contact information can be found on the brainsmatter website. The theme music Soul of the Machine was composed and performed by Clive Weeks and is used with his permission. I hope you enjoyed the show. Bye for now.